Good day, ladies and ladies. Right, we're now working with indeterminate limits. A big word like marmalade meaning something very simple. Remember that when we were finding the values to start with, when you were finding them in class, maths class, first option is to substitute the value towards which the said variable is tending and hope that it comes out simply. Let's take a couple of examples. Here we are. Limit of x plus 3 as x tends to 2. Well, I'm just going to substitute 2 in for x. So I have 2 plus 3, which is 5. Yippee, that's solved. Looking at the next one. Limit as x tends to pi by 2 of sine x over x. So I'm going to substitute and hold thumbs. Sine of pi by 2 over pi by 2. Sine of pi by 2 is 1. Remember, pi by 2 is 90 degrees. Sine of 90 is 1. And this will invert and we end up with 2 over pi. So those are quite acceptable. Oops, I'm sorry, I'm getting trigger happy here. That's better there. Okay, so to continue from there then, let's have a look at a whole lot of these. Looking at this first one, if I substitute pi for x, I'll get sine of pi over pi, and sine of pi is 0 over pi, which gives us a 0 over non-zero. So that's the first type of limit I could consider involving zeros or infinities. This next one, limit as x tends to 0 of e to the x over x. Well, e to the naught, e to the 0 over 0. That gives me 1 over 0. So here's the next category, non-zeros over 0. Looking at the next one, substituting 0, we'll have sine of 0 over 0. There you are. Which is 0 over 0, which is the next sort of category. Next one, tending to infinity. 4 over infinity. So, there we are, 4 over infinity. So this next one, a non-zero over infinity. This final one, if I substitute infinity into these, very, very big, I'm going to end up with very, very big top and bottom. They might not quite be the same. That's why the limit may not be 1. So, that's an infinity over infinity, and that is another category. So, that first one, equal to 0. Non-zero over 0, non-zero over 0, well, can't be done. So therefore, no limit, but when you're doing tertiary maths, they no longer speak of no limit, they'll say the limit is infinity. The next one, 0 over 0. Right, this one's a problem. You know, if you had one like that, then you'd go back and try to factorize to simplify it. So that's exactly what happens here. Further algebra required. We cannot determine it at that stage. This next one, non-zero over infinity. Well, the top is constant and the bottom is as big as you want it, so therefore that's going to end up as 0. And the next one, infinity over infinity, it's the same as the 0 over 0. It actually tells us nothing, and we've got to do something about it to be able to see. And that's where we'll end up with the same answer, further algebra required. Now that we've done all the nitty-gritty of it, let's get into what we're due to be doing. That's the indeterminate form. There we are. They're called the indeterminate form. Those two forms. Substitution doesn't give enough information to determine the original limit. Here's some more examples of indeterminate form. If you look at these, some of these are a bit weird to think out. 0 times anything is 0, but what about infinity? Infinity minus infinity, well, are we sure they're both the same size? 0 to the anything is 0, but anything to the 0 is 1, so we have a dilemma there. 1 to the infinity, I think that's 1. I don't know that that's indeterminate, but infinity to the 0, I think that's probably also 1. But anyway, this is the sort of thing you get with indeterminate form. We're not going to worry about that. We're only going to worry about the 0 over zeros and infinity over infinities. Tending to infinity. It's a concept, not a number. Describes anything, something without any bound or larger than any number. So, for example, if n is an element of R greater than 0, then the limit of x to the n as x tends to infinity has to be infinity. Alright, so that's what that tells us. No matter how large any given number k may be, the value of x to the n will eventually exceed it. Why an element of R? Well, even if you have 1/3, for example, that's fine. That's cube root. It's still becoming bigger and bigger, infinitely bigger. The only thing it can't be is negative. In fact, here's an example. Y greater than 0? Well, if it was less than 0, for example, if we have -2 here, then we'll end up with 1 over x squared. Now that's becoming infinitely large below, which means I'm going to go towards 0. That brings this different case. Same conditions, the limit of 1 over x to the n as x tends to infinity is now 0. The limit of 1 over x to the n as x tends to negative infinity is also 0. In fact, it alternates because it'll be positive, negative, depending on the numbers, etc. But the important thing is x tends to infinity. Now, this is just theoretical stuff, really. Don't worry too much about it. It's just to give you a bit of background. But the actual nitty-gritty main stuff in it is what comes now. Called L'Hopital's rule. I didn't draw that. Right? Useful tool for finding limits of the indeterminate forms 0 over 0 and infinity over infinity. Doesn't matter how you pronounce it really. It's pronounced L'Hopital usually, even though it's spelled L'Hospitals. Often spelt L'Hopital and often pronounced L'Hospital. What it says is, if a limit is indeterminate, this is all you have to look at. Don't worry about that, in fact. That's just the theory. The limit of f of x over g of x as x tends to infinity is equal to the limit of f prime of x over g prime of x as x, did I say infinity? I meant alpha, is equal to the limit of f prime of x over g prime of x as x tends to alpha. So if and only if we have an indeterminate form of 0 over 0 or infinity over infinity when we substituted and f of x over g of x, then what we can do is we can differentiate the top and the bottom and continue like that. An example. sine 2x over 2x. If I substitute 0 into those, I'm going to end up with 0 over 0. So therefore it is indeterminate. So now I'm going to differentiate top and differentiate the bottom. So there we are. This is a chain rule. Outside function sine, so it becomes cos, and it's still 2x. Inside function stays the same. Multiply by derivative of the inside function 2x, so it's multiplied by 2. All over 2x. Now, there, if we simplify, from there, substitute 0, we're going to end up with 2 cos 0 equal over 2. And cos 0 is 1, so we're going to end up with 1. Here's another 0 over 0. Limit as x tends to 0. Well, cos of 0 is 1. So it's 1 minus 1 over 0. So I'm going to differentiate again. Derivative of cos is minus sine. And the 1's going to go. So I'm going to have the limit as x tends to 0. And I'm going to have minus sine x over cos x. Now if I substitute the zeros, I'll have 0 over 1, which is 0. Another substitution. Once again, if you substitute 0, you get 0 over 0. So I'm going to differentiate top and differentiate bottom. And if we substitute now, we're going to end up with 3 minus cos of 0, 3 minus 1 over 1, which gives us 2. Next one. Alright, that one's virtually impossible, really, without this. But, here we go. If I substitute 0 into there, I'll get 0 over 0. Indeterminate. So I'm going to differentiate top, differentiate bottom. Notice you don't have to look at this as a quotient rule. It's not. It actually says limit of the top, limit of derivative of the top over derivative of the bottom. So we differentiate top and bottom separately. Please don't think that I'm now just assuming I can differentiate numerator and denominator separately. But in Hopital's rule, we do. So I'm going to write this in a more differentiable form, first of all. There it is. Now, if I differentiate the top, it's something to the half. And that something's 1 plus x. So it's half 1 plus x to the minus half. That goes. Times derivative of the inside, which is 1. So we'll end up with that on the top line, 1 on the bottom line. Now if we substitute 0 into that now, this is going to be 1 to the minus half, which is 1. So our overall answer is going to be that, which gives us a half. Once again, with pi by 2, if I substitute, I'm going to get 0 over 0. So I'll now find the limit of derivative over derivative. Substitute the pi by 2, and sine of pi by 2 is 1. So therefore, I'll end up with minus 1. Here's a limit going to infinity. Now if I substitute infinity into top and bottom, I end up with infinity over infinity. infinity over infinity. But I can differentiate top and bottom and keep going on the limit. So therefore I have that now. Derivative of the top, 6x minus 2. Derivative of the bottom, 2x minus 4. If I substitute, I'm going to find it's indeterminate still. So I still am not able to find the limit. But all I do is repeat the process. I'm going to use L'Hopital's rule again on that. There we are. Which means it's a constant, and therefore the answer is 3. Finally, a big warning. Big warning. Beware of the L'Hopital. Beware of the L'Hopital. Consider this. Given f of x equals x squared plus 6 and g of x equals x squared plus 2. If I say limit of f of x over g of x as x tends to 2, which means that, then I'm going to substitute it and I get 3. Now what happens if I use L'Hopital's rule on it? I'm going to differentiate top and bottom instead. So I'm going to say 2x over 2x, and I end up with 1 different answer. Why is that? Consider that. Simple reason. It's not indeterminate. This is not indeterminate. There, we see it's not indeterminate. It's got to, L'Hopital will only work on limits with 0 over 0 or infinity over infinity. So after that, here's a little fun practice. Some are going to end up with infinity over infinity, others maybe with 0 over 0. Sometimes it might not be either. Sometimes it'll be a straight, normal limits question. So just be careful. The answers do follow, and it's also on your printout.